Dr. Sikha Hota. Dr. Sikha Hota received her BE degree in Electrical Engineering from Indian Institute of Engineering, Science and Technology and ME degree in Electrical Engineering from Jadavpur University. She did her PhD in Aerospace Engineering from Indian Institute of Science in 2013. She worked in National Claw Team for LCA on behalf of CSIR NAL. Since 2015, she has been with Indian Institute of Technology, Kharagpur, and is currently an associate professor. Her primary research focus is on guidance, path planning, obstacle avoidance, collision avoidances, autonomous control of unmanned aerial vehicles, and multi-vehicle coordination. Thank you, Dr. Shikha. Now I would like to invite you onto the stage.
Good afternoon. So, first I would like to thank Professor Ratno and team for this wonderful initiative, which will remain with us forever. And I'll be talking about waypoint following by unmanned vehicles. So, before going to technical talk, allow me to express my sincere gratitude to my guru, Professor D. Ghosh. Whatever I have done, it is because of him. So, the work is about waypoint following. So, first, what do you mean by waypoint? Waypoint is nothing but point of interest. So, it can be something like that, a point whose latitude, longitude, altitude is given. It can be a building. It can be a kind of a military base which should be observed, or it can be a very crowded place which should be monitored. So, the best way to monitor is, representation, pictorial representation is here. So, best way monitor is starting from any location converts to a circle, okay, of given radius. So, idea is to that generate a trajectory of this kind, so which is applicable from any initial condition and orientation. It should come to this loitering circle as quickly as possible. I mean, it should be time optimal. At the same time, as we are considering here the vehicle which is of non-holonomic type, okay. So, there are some kinematic constant, for example, turn radius constant, if we consider two-dimensional path planning algorithm. So, it should obey all these constraints and converge to the circular path. So, there are many approaches in literature. You will see it comes under the topic of standoff target tracking, okay. So, one of these approaches is vector field approach, which I am going to discuss in detail in today's presentation. See, vector fields are nothing but the heading angle at every each x and y, okay, if it is 2D. And if it is 3D, then every x, y, z, that flight path angle and heading angle will give the velocity vector. So, that should be specified. And the idea is the vector field should be constructed in such a way, finally it will converge to this circular path, okay, which is given. And it can be done in the presence of wind also. In the presence of wind, these angles will no longer be heading angle. That time it will be course angle. If you see that velocity triangle, that air speed and wind speed, it will make that ground speed. So, the course angle will be with respect to that Vg and true north direction, that angle will be course angle. So, it can be easily extended in the presence of steady wind. So, that is the idea. And so, now consider there is series of waypoints. So, sequence of waypoints, some starting from 1 to some n number of waypoints are there. So, then first what we have to do is converge to the first segment. Okay. So, consider this is W1 and this is W2, first two waypoint segment. So, starting from any location, we need to converge to this straight line path. So, this comes under another topic, the straight line path convergence. Here also idea is same, starting from any location and orientation, so the position and orientation is given. So, it should converge to the straight line path and then track the path. In this case also, we are going to construct this vector field method and see the heading angle will be given in such a way, finally it will take you to the path, the straight line path segment. Then, as we are considering the number of waypoints W1 to Wn, After converging to first waypoint segment, idea is to converge to the next waypoint segment. So two consecutive waypoints are considered, that wi minus 1 to wi. Suppose it was following this straight line and it has to converge to the next waypoint segment, which is denoted by wi to wi plus 1. So that transition also should happen in a very smooth way. Okay, as I mentioned that it is for non-holonomic vehicle, at least we should provide C2 continuity. So what do we mean by C2 continuity? We know that C1 continuity means the tangents are continuous. C1 continuous path can be made out of circular turn and straight line turn. But if we consider non-holonomic vehicle, we have to give C2 continuous path for which curvature will be continuous. So I'll show it in next slide. So here see number of waypoints are given, W1 to Wn, and the sequence is given. Okay, so it should follow the waypoint segment and transit to the next waypoint segment and complete the entire task. That is our final goal. So the UAV will be the unmanned autonomous vehicle, and the approach we will be considering here, that hierarchical control approach, not the integrated one. In hierarchical control, there will be outer loop structure and inner loop structure. Outer loop will give the guidance command and inner loop will give the force, and it will generate the force or moment. Basically in this code, in this work, I am going to present this portion, okay, guidance, that outer loop guidance path. Okay, so a quick review of the literature. So there are many existing algorithms, as I mentioned, that it comes under that waypoint following or stand-up target tracking or circular path convergence. Okay, first one to consider this optimal geometric methods, and then virtual target chasing, point chasing method, and then stable attractor based method. These are the few names what I am going to discuss later. So optimal path following algorithm using Dubin's path, that is the geometric path. Okay, this already morning you have seen that in Suresh's work it was mentioned. So this path can be, if the point orientation, as I mentioned, this is waypoint following problem. So suppose there's first waypoint and orientation and second waypoint and orientation, this is specified. Then what will be the optimal path? That if they are well separated, we call it greater than 4 hour, then you will get the CSC path. C means that it can be that right turn or left turn of minimum turn radius. So it can be RSR, RSL, LSR, LSL, like that. Or if they are close, they are very close, then we will not get the tangent in between. We have to, that optimal path will be CC type. Okay, CC type can be RLR or LRL. Okay, so this was proved by Dubins in long back, okay, 1957 by geometry, but later using optimal control theory, so specifically point range minimum principle was used to prove this result. Same result they have obtained in 1994. Okay, so there it was kind of time optimal. The performance index is that we have to minimize the time to reach, and the state equations are kinematic equation of the vehicle, and then the proper formulation, you know, that's optimal control formulation, and it is kind of bounded control. We have, see, the vehicle is with bounded turn radius. Okay, so that constant if we apply, then we'll get we can reproduce the same result. So this work was using this path, straight line convergence and that stand-up target tracking problem was solved earlier, and then this work was extended in 3D during my PhD time. It was basically 3-dimensional, the CSC path. Initially, I was struggling with this, how to get this, because you know that in 3D when orientation is given, so there are many circular turns possible. Then professor suggested me, you take bangles, next day you come with bangles. So next day I came with few bangles, so I was trying to visualize how to get these turns, how to get the tangent, and finally we obtained this. This is that's the circular turn, straight line turn, and final circular turn. But today will not be discussing this one, because this one will ultimately give you C1 type of path. Okay, as I have mentioned, see, this is the limitation. So C1 path means that initial circular turn, straight line, that final is also circular turn. You will see the turn rate. It will suddenly jump from high value to that the maximum value to this 0 value. Because of that, curvature discontinuity will be there, and this cannot be implemented for non-holonomic vehicle. So this sorry this result is for straight line convergence. Okay, this work was done during my PhD. This was done in the presence of wind also, but here recently we have submitted a paper where we have modified. We have not used this transition, rather the transition is done by this sinusoidal pattern. Okay, and you can see that now the curvature will exactly follow similar kind of profile. So you will see the curvature will be of C2 type. It is a smooth curvature. I can show you the simulation result. So this blue one for a particular configuration, the blue one was Dobbin's path, and red one is the recently produced result. And yeah, if you see the path length, it is, of course it will be little more, okay, but that is acceptable as we are getting C2 type. And same work is extended for stand-up targeting for circular path convergence, but I have skipped that result, okay, for brevity. So curvature, see the curvature profile, this is very smooth and easily implementable. Later I will discuss this. If we compare the similar kind of work like our already Professor Ratno's team, they have several papers on this. Okay, we have compared that result with Nelson's work. This Nelson note I will show it later also. This was the first bunch of paper what Prof gave me, 10 journals, and after 1 week he asked me to meet and I couldn't understand anything. Okay, so this was my first paper. It was by Nelson and Lord, vector field path following. So that also I am going to show you later. Okay, so that was the geometric path, geometrical based on basically Dobbin's path, which is we can say that was proved by optimal control theory, that is optimally concrete optimality proof is there. But next I will be talking about some virtual target point based method. One of them is L1 guidance. This is very interesting work which was published a long back, but still many improvements or many variations of this L1 guidance, okay, we can see that in recent literature. So idea is if it is the desired path, and in the UAV is somewhere else, so it should converge to this path. So a L1 value should be selected. Okay, later I will comment on that L1 selection. So based on this L1 selection, that R can be computed. So see, L1 and R, they are related in this way. From the geometry it can be easily understood. And for that the acceleration command will be this square by R, which is nothing but this command. So if you apply the command and if you update your current position and orientation, ultimately in this way it will take you to the path. If it is a straight line path, the demonstration is this, it is shown in this. But the critical point is how to select this L1 value, because if you select higher value of L1, then we will get non-optimal trajectories, and smaller L1 will cause no solution. You can see that high L1 value, that is blue lines, okay, it is non-optimal, and low L1 means it will be kind of, and even lower value it will not converge at all. Okay, like straight line path following, you can see from this, and for circular path following, see, it can be seen from here, same effect. But recently my students, they have worked on that and they have optimized this, and they have made optimal L1. The results are not included because it is not communicated yet. Another VTP based approach is that carrot chasing algorithm. The idea is very simple. So this UAV's current position is here, and this is the waypoint segment Wi to Wi plus 1. Now you draw a perpendicular, which is the distance can be denoted by d, and you have to select a delta value. Again, delta is designer choice. So based on this delta, you need to calculate that psi d, the desired one, and this is the current one, psi is the current one. So your command, the control command should be this, k into psi d minus psi a into va, and this will take you to the path. Again, it is dependent on delta value. So aggressive navigation due to small delta, if you consider small delta, see there is lot of oscillations before convergence, and if you consider larger delta value, it will take long time to converge. And again, this is one paper recently published. They have used pattern search algorithm where the delta is optimized to converge to this waypoint segment, and then the n number of waypoints they have considered using this optimized delta value. And this work is compared with this optimal L1, and you can see the result for a same turn rate, okay, there's carrot chasing is not having any overshoot, but L1 is having little overshoot, and the rise time is less. You can compare in this way. So these are the methods which is used heavily for this waypoint following problem. Another method was pure pursuit and LOS guidance law. So basically that if it is the waypoint, first waypoint, if it is the second waypoint, then again the perpendicular is to be constructed, which is d distance away, and what we have to do here, control command will be k2 into d and psi theta d minus psi into k1. So in that way, if you generate, again the path convergence can happen. The simulation result I have not included here. So these are the well documented result. Not recently, our team member Dr. Shujit, he has published a paper, okay, where all these methods were simulated nicely and compared. Okay, so all were VTP based approach. Now let us come to the point of vector field guidance, which I am going to focus. So this is the paper what I was talking about. 2007 I joined my PhD, and that time this was published. So this was basically this work was done for straight line convergence and circular path convergence. Straight line convergence, the idea is, see that you need to this is the desired heading command. So desired heading command is minus chi infinity 2 by pi tan inverse k y. So basically this is y is that lateral distance error. Idea is, if you are very far, then come perpendicular to the straight line, okay, that is the best way, that will be the faster approach, and when you are close to this the line to be followed, then try to align along that. So this equation will exactly fit that, okay, and based on this k, different values of k, convergence rate can be changed, okay. K, for small k value it will take long time, for k that larger k value it will take lesser time. So from there we started our work, and then we included in this work turn radius constant was not included, later turn radius constant was included, and for the straight line convergence and circular path convergence. Circular path convergence, okay, let me tell you the idea. Again, when it is very far, then come the orientation should be, it should be reoriented so that it is pointing towards the center of the circle. So that will be the first way to convert. Again, when it is close by, then again that align with this means the tangent will be the common tangent, which is the small circular turn, and this is the circular path to be followed. So in that way it will converge. So this is the first paper on this path convergence. But using this method, the limitation was it is only applicable for straight line convergence and circular path convergence. For elliptical and for other shape, there was some error. So later this method, this is another vector field method, okay. This is Lyapunov vector field guidance method. This is little different from whatever was proposed in earlier case. Earlier case, just vector field was selected, and then using Lyapunov function the stability was established. A suitable Lyapunov function was found. Here it is just other way. Here first that we have to suppose this circular path to on which that UAV will convert. So then that Lyapunov function should be chosen like this. So x is that x position, y is the y position, and this is the radius of the desired circle. So if you choose the Lyapunov function and that propose some vector field, using that, if you can show that dv by dt is negative, then actually you are done. Then definitely it is going to converge to this circular path. It will behave like a stable attractor, which you know from the Lyapunov stability theorem. And using that, this vector field is proposed. Okay. Then after that, there were several variations of this Lyapunov guidance vector field method. Okay, another work, this is very popular work, because using this method, this was done by Liang 2016. Using that this method, not only circular and straight line path, okay, it was done for kind of Bezier curve, sinusoidal path, even star also we can convert. Okay, the idea is, see, they are this solenoidal, this is the this guidance vector is represented as sum of conservative and solenoidal fields. So this is the conservative fields, so it will take you faster, okay, and this is the solenoidal field. it will help you to orient along the path. Okay, if you use the combination, some kind of k1 plus k2, some weightage, if you put, later I will show you what kind of weight function can be considered, you will get the vector field, and it can handle all kind of kinematic constant, okay, like turn radius constant and all. Okay, so this work was more generic, and as I mentioned that as scaling term we can use the tan hyperbolic and sec hyperbolic. Seeing this profile, you can see that change is very smooth, and if you use it and normalize it, it will give you a nice vector field, and with different turn radius constant it can be implemented. Then again Professor Ratno's group, they have done excellent work. They have done curvature constant Lyapunov vector field guidance. Okay, so here before that the curvature analysis was not done. This was the first work which considered the curvature analysis also, and using that they have shown that I have not included the curvature profile, so it has nice peak and it is going down, so it will converge to the circular path from even if it is very far, or even if it is that inside the circular path to be followed. So this work was done by my PhD student Horinarayana. We also have considered that exponential function like this, and contraction component and circulation component is based on this exponential function that is decomposed in odd and even function. And again we have constructed some little that algebraic manipulation, and we have calculated xd dot and yd dot. This will actually provide the direction, okay, heading direction. And here also using Lyapunov function, that it can be shown that the circle will behave like kind of attractor, stable attractor. And the idea that why it is different from other papers means the idea came from the Dubin's path. From Dubin's path, if we analyze, we know Dubin's path is the optimal path. The main limitation was Dubin's path is having C1 continuity. So what we have done is, from Dubin's path we have plotted the circulation term and means both the terms, solenoidal component and conservative component. Okay, so from that we understood that that if we choose the that was having kind of discontinuous behavior, sudden jump, so that curve we have made it smooth. Okay, after making that smooth curve, we are getting this, and it can be, the stability can be established, and we can consider different turn radius, that constant vehicle. Okay, suppose the vehicle turn radius is some r min 1 or r min 2. Okay, so based on that we can design the path. So it is applicable for any vehicle. So this is the comparison. The target is here, and this is the proposed path. This is represented by blue, and this is by other methods as I have discussed. So you can see that convergence is means it is optimal, means close to optimal. I should not say optimal, because it is following Dubin's path, but it is having C2 continuity, so close to optimal. So it is touching the this is your curvature plot. So the curvature value, the highest peak value, it is touched. If it is inside, the simulation results are shown here. Okay, now that was for single waypoint, so you are loitering around that. Now if you consider the n number of waypoints, as I mentioned, first work will be to converge to the first waypoint segment. Okay, first waypoint segment is represented by W1, W2. So to convert, this is the kinematic model. Okay, so first converge to this path, and this is done by this vector field. Okay, the stability is again ensured, and this will behave like equilibrium, so it will take you to the path, and see for any tilted that straight line the work is done. And then as I mentioned that in number of waypoints are there, so once you converge to one waypoint segment, next work will be to converge to the next waypoint segment. So that is done in smaller. This is also adopted from Dubin's transition. So Dubin's transition means just single circular turn. If you fit in between, so it will take the straight line path, then circular turn, and then that straight line path. But that is replaced by this kind of C2 path. The detail is here. Again, that stability is ensured. We have here that these are the selection of components. Okay, convergence term and circulation term. Okay, so this is the figure I was mentioning. For Dubin's path, you will get this kind of behavior, convergence term and circulation term. See, there is sudden jump. This is not smooth. So this motivates us to take some kind of this kind of function, which will be smooth as well as close to optimal. Okay, we also have done the curvature analysis. So curvature is computed in this way, and here see in the proposed field we have kind of a constant. Okay, c can be chosen for that optimal that curvature value. So we have done this optimization. So we can find c, and c will be different for different vehicle. So in that way it can be applicable for any vehicle. So this is the experiment we have. Yeah, so I need to mention here quadrotor. Of course it is holonomic vehicle, it is not non-holonomic vehicle, but we have done the experiment because it is in indoor setup. Okay, the experiment is done very easily. And another thing is that even if means quadrotor, you know that it can go sideways, but if you provide a smooth path, the tracking will be really better. That we have seen when it is joining waypoint segments, and when it, the quadrotor was trying to track, there was lot of oscillations. But when we have given the smooth profile, which was designed for non-holonomic case, but the tracking accuracy was quite better. So you can see the part. If time permits, later I'll play the video. I'll just keep the video for time being. This is the experimental result. Okay, later I'll try this. Okay, this is for another test case. I'll just keep. Okay, this work was then extended for 3D, because you know 2D means the altitude was assumed to be constant, which is done through some autopilot. But if you consider 3D problem, so that will be more generic and that is close to real life implementation. But the idea is very simple. If you join two consecutive waypoint segment, basically one plane can be formed. Okay, so whatever work we have done in 2D on tilted plane, just with the rotation, it can be easily implemented. That's what is done. So 3D implementation videos are also there. I'll skip it for timing. Okay, so this vector field work, the advantage is that obstacle avoidance can be easily incorporated. See, if we construct this kind of function, so this is the orientation of the vehicle. Okay, this is the UAV. So actually I have written here virtual leader, because basically the work is done for a formation. Okay, so the work is applicable for single robot also. So the function is like that. The sec hyperbolic function is used. So if you are close to this is the obstacle that is of radius r0, and this is L distance away from the center. So if L is close to r0, that means it will have higher value. And similarly here theta gamma, when they are close, that means obstacle is on the way, so it will give higher value. And based on this we are changing the heading angle. Okay, the new heading angle is heading angle plus this, so it will give you very smooth change. As you can see here, the goal location is at this place, and vehicle started from this location. So it will follow this function, change its heading angle, and take the turn, avoid the obstacle, and come back to the goal location. It can be easily extended for multiple obstacles. The equations and all I have skipped, but it has been done for this multiple obstacle, even for dynamic. This was static obstacle. It is done for dynamic obstacle also. And using this vector field method, as I have shown, that the obstacle avoidance also, and it doesn't have any singularity. Many obstacle avoidance problem, the main problem is singularity. So we avoided that. Another work which is not published yet, that using this vector field we have achieved the formation. So see the formation with 3 vehicles are shown here, starting from any location. They are making triangles, and there are dynamic obstacles. See, these obstacles are dynamic obstacles. There are static obstacles. So avoiding all this, okay, they are able to explore all the waypoints. Okay, this result we have not published yet. Okay, and we are making it for up to 6. It is working. Okay, still we are struggling, because when number of vehicles are more, there is a possible of collision, intercollision. So that we have to see further work on this. Okay, this is the result for formation, that same simulation result. Okay, these are some references which I have shown in the slide. So this is most memorable moment, okay, during my convocation. I was standing, I got a chance, I was jumping to stand here. Okay, so thank you, special thanks to my students who helped me to prepare the slides and the simulation animation.
Thank you, Dr. Shikha, for that wonderful talk. We could take a couple of questions before proceeding to next talk.
Yeah, hello. It's a nice presentation. I just want to know one thing, that in the case of like obstacle avoidance, you use some sec hyperbolic function.
Yeah.
So I just want to know the motivation that
actually,
for selecting that.
I have
particular
shown you
function.
the sec hyperbolic profile. So it is very smooth. Okay. So based on the difference between that L, that the distance, and R0, R0 means that radius of the circular part, that turn will be very smooth. Okay. It will not take sudden turn.
Like there
So
could
that
be other
motivates-
function which we can get.
Yeah,
Is
there, see, in obstacle avoidance, many approaches are there. This is one approach, and here we have seen that it is singularity free.
Okay.
It can be shown because if you have seen the literature, many are having the singularity problem. Do
Okay.
not get the vector direction there.
Okay, thank you.
Any more questions?
Okay, then I can play a video if you allow me to
Yeah,
do
sure.
that. Can you go back from the study? At least for 3D, 2D, this is fine. Okay. I'll just show one. Maybe sound will be an issue. Huh? Sound is
I have reduced it.
reduced. Okay. Okay, thank you.